Okay, sorry for the delay in getting started. I had a little bit of trouble getting the live stream going, but regardless, welcome to the live stream this evening. What we're hoping to do is actually catch a glimpse of the James Webb Space Telescope as it's traveling through space on its way to the L2 orbit point. Okay, had the telescope set up. I just took a little test image of M42 just to make sure everything was good, the focus was set and everything. So as you know, the James Webb Space Telescope was launched about 2 weeks ago, and it's on its way to the L2 Lagrangian point where it's going to orbit and do its work. It's going to take roughly, I believe, a month to get there, and in the process it's slowly unfolding the telescope. I'm sure if you've seen the videos that it's made up of segmented mirrors that are all folded and tucked away upon launch, and then has to kind of unfold and put everything together to form the mirror. So it's in the process of doing that right now, and I understand it's everything's good and successful so far. So let's hope it keeps going that way. Okay, so the first question you need to ask is, where do you look to see the space telescope? And up here you can see I've got the coordinates in here. Now I obtained these from the JPL web interface called Horizons, that you can get the coordinates of just about anything in the solar system and display it relative to your position on Earth. So this is what it at 7 o'clock, so 8 minutes ago, this is the coordinates that was here. So let's go ahead and slew the telescope. Let's go there. So the telescope is currently slewing to that position. And once it gets there, it's going to take a quick snapshot to identify the stars in the field of view. It's going to do what's called a plate solve, which means it's going to align all the stars in the image and compare them with the catalog entries, the known entries for the stars, and then it'll determine how far off the telescope is pointing, and then it'll do a correction and then repeat it. Okay, so it's taking the second image right now. You can see, and it found 649 stars, and it says finished. Okay, and there's the field of view right there. Now the tricky part is we're going to take I think a sequence of images and see if we can see any of these stars that are moving. So let's go ahead and take a 30-second exposure. Okay, so there's one 30-second exposure. So let me go ahead and take a sequence of 10 exposures, and then I'll download those to the computer that I'm sitting in front of and use a tool in PixInsight called Blink. So it'll actually animate the images so you can compare them side by side and look for a moving object in there. Because obviously with this, the number of stars in here, it's going to be very hard to identify, you know, just one of the small dots moving. So let's go ahead and go to the plan here. Well, let's not do the plan. Let's do an auto run sequence. So we'll go ahead and take 30-second exposures, and I'm going to take 10 of them. And they're light frames. Okay, and James Webb Space Telescope. Okay, before we do that, let's go ahead and get the auto guider going. So those are the stars that are visible in the auto guider with a 2-second exposure. Okay, that's doing a multi-star guiding, so that should improve the results. And let's give it a moment to settle down. Okay, we got roughly 2 arc seconds of guiding error right now. That's not particularly good, but it should be good enough for what we're doing here. So let's go ahead and get that sequence going. And while it's doing that, let's go ahead and I got a couple of pictures of the setup, so let's go ahead and take a look at that. Now this is the observatory here. It's a 12-inch Meade LX200. It's the telescope's probably about 20 years old, so it's not obviously state-of-the-art, but it does a job. And what we're looking at here, okay, this is the guide scope right here. It's a kind of looks like a 63 millimeter Brandon that was made years ago, but it's, I believe, actually made from parts that were used in the original Brandons. So it looks like a Brandon. And what we've got a diagonal here, and then the guide camera, which is an ASI 224 MC guide camera. Now the right hand prism is required to allow everything to be put on the telescope, because if I didn't have the prism in here, this would be hitting this next item that you see on here, which is the ASI Air Pro, and it's a computer that's controlling everything that the telescope is doing right now. So that interface where we're going to and absolutely controlling the telescope is all being done by this device here, which is connected via Wi-Fi to where I'm located. And down here, this is the main camera that we're using right now. It's a ASI 294 MC Pro camera. It's not top of the line by any means, but it's a one-shot color camera, so you're able to instantaneously get color images without using filters, as done with more of the advanced astrophotographers. And this is the ZWO electronic focuser that we're using, so we can actually focus it remotely as well. Here's an electronic focuser. And this is the hand controller for the telescope here. Now this is, I mentioned that the telescope is 20 years old, but the electronics have been upgraded by a kit that was developed by a gentleman by the name of George Dudash. So it actually take the old electronics out, put his electronics in, and you got immediately an upgraded telescope that uses the latest Meade technology. And this is the Meade Audio Star hand controller here. And there's what everything looks like stacked on top. And there's the back end there. And a close-up of the guide scope. One thing you'll notice on here, up in front here, this is actually a small heating element that is used to keep dew from condensating on the objective lens. Because when humidity does get fairly high around here, then you'll have condensation on the lens, and your observing session is pretty much finished at that time. And you'll notice that there's another one up here for the main objective of the 12-inch. And just some more views of it. Okay, let me go back to the beginning here, where I didn't show you this one here. Now here's the observatory, and what I've got one of the mesh Wi-Fi systems set up out here to give a stronger signal strength to the observatory. So between the observatory and here, it give me increased performance with the downlink speeds. Okay, so let's see. Okay, it looks like we're already finished with all 10 of the images, so let's go ahead and download them here. Let me okay, it looks like they gave it an M45 name. Okay, so starting to copy the files right now. It'll probably take a minute here. Okay. Yeah, hi Jim, I'm glad you're able to join us here. Yeah, I just finished a sequence of 10 images and I'm downloading them right now. So hopefully we'll see something here in a moment. So, you know, one of the aspects of astroimaging is you have to have a lot of patience. Nothing happens quickly. If you're looking for, you know, fast, exciting events, then you're going to be disappointed. But hopefully, all of our people here, astronomers who are interested in, you know, astrophotography and have some experience, so they can, you know, have a better sense and understand, you know, what's going on. So I'm going to go ahead and open PixInsight here. And use a tool called Blink. Okay, I'm opening up those images. Okay, let me bring up PixInsight on the screen for you here. Uh-oh. Okay, sorry for the delay. I'm bringing up the images here. Looks like it's not displaying the PixInsight screen, so let me move it over here to this monitor here. And let me see if I can zoom in a little bit. Not quite doing what I wanted to do, so bear with me. But anyway, I got those 10 exposures loaded up, and I'm blinking it right now, but I'm not seeing anything moving. Okay, I didn't see anything blinking in there. Let me try one thing here. Let's go ahead and confirm that we've got the right field of view. We'll do that by going back to preview. We'll do a plate solve. And 632.17 plus 139.17. So we're not that far off. We're about 1 arc minute. So let me go ahead and double check the ephemeris to make sure it hasn't moved that much, and let me go ahead and see where it should be now. Yeah, looking at the ephemeris, it looks like it's moving surprisingly slowly, because in an hour it's only moving roughly 30 arc seconds in an hour. So that's in the 2 minutes that it took to download those 10 images. We're not getting a whole lot of motion, so let's go ahead and wait, and then go ahead and get another sequence and compare it, because as time moves on, we'll be able to see more motion. Let me see. So here's the image. I've enlarged it a little bit so you can see kind of what it looks like as the image is being animated. So it's quickly going through. There's 10 images in this stack here. So it should be roughly right here in the center. But I'm not seeing anything right now. So let's go ahead and take another sequence of 10 images and do the same thing. And let's see if that improves anything. So let's go back to the ASI Air Pro. Okay, it looks like the auto guider is still doing a decent job of keeping it centered. Yeah, Jim, you asked what the magnitude is. The last reported observations from I think a day or two ago was showing it around 14th magnitude. So that's well within the capability of this instrument here. I think what we're seeing typically for near-Earth asteroids, your skyplane motion is actually a lot faster. So when you do animate images, sequences like this, you can see immediate motion in between. So let's go ahead and go back to our auto run and redo the sequence, another 10. So that'll take about 5 minutes. Yeah, I'm just double checking all the coordinates and everything for the positions that I retrieved from the JPL Horizon system. So right now it's about 3.5 hours after midnight on January 9th, Universal Time, and that's what the ephemerides are presented in. Let me Okay, looks like we've got 3 images taken so far. And I'm double checking the ephemeris from the JPL site, and I think I discovered something that might be a problem. So I'm with respect to the reference frame that the ephemeris defaults to. No, I don't think that's it. And it looks like the ASI Air Pro is invoking the autofocus routine because of the temperature change. That's gotten 2 degrees Celsius cooler than when we started, so it's going through the autofocus, so that'll take a couple of minutes for it to complete that. But okay, now it's continuing. No, I was thinking that I had a problem interpreting the ephemeris, but I don't think that's the case because the positions that I'm getting from the JPL horizon side are consistent with what are being reported from other astronomers. I think it's just moving very slowly relative to the background stars right now. Okay, it looks like that sequence is completed. So let's go ahead and copy those. To the computer here. Okay, it's almost halfway through copying the images. Okay, they finished copying. So let me go ahead and bring it up on. Over Pix Insight. Okay, let me go ahead and blink those. Let's go ahead and zoom in and see if we can. Let's see, one bad image there. Actually, a couple. Okay, so now we'll just blink quickly between the two image sets. And roughly the center is here. So I'm not seeing it. And it'll help if we do a star alignment on the image sets here. But I'm not sure I want to do that right now. So let's wait a few more minutes. Actually, why don't we go to the M45 and do a live stack, and then we'll come back to the James Webb Space Telescope field, and more time will have elapsed, and hopefully the motion will be detectable then. So let's go ahead and come back to here. Yeah, Jim is asking, given the size of the space telescope and the distance, that it will only show up as a point starlight source in the image, and that is true. It's far away. It's not like the International Space Station that is actually close enough that you can actually resolve the size of it in some of the Earth-based photographs that have appeared taken with amateur telescopes. Okay, so let's go ahead and stop the autoguider. And that's sort of like a parking brake on a car. If you slew the telescope with the autoguider going, that's not going to end well. So let's go ahead and go to preview. Let's find a target. Let's see, M42. And let's go to it. So the telescope is slewing to M42, which is actually fairly close to where the James Webb Space Telescope is. Okay, it's taken the second image right now. Alright, so there's the, that's what it looks like right now. This is just a short exposure. Let's go ahead and, that was a 5-second exposure. Let's go into the live stack. Let's go ahead and get the autoguider going again. And go ahead and get it tracking. And we're waiting for the settling. Okay, that's pretty good. So let's go ahead and save them while we're stacking. Darken bias. I don't have any darker biases on the or at the telescope on that computer, so we won't do that. We'll save that for post-processing afterwards. And let's go with 1 minute exposures. Why this thing's not not easy to select. There we go, finally. Okay. Let's go ahead and clear. Now let's go ahead and start. So what it'll do, it'll take 60-second exposures, and as each one comes in, it'll stack it on the previous image that had come in to build the signal to noise ratio. So with each subsequent image, you should have a stronger detail in the outer wings of the Orion Nebula here. Okay, we got auto histogram, so that's what we want. Okay, so it's downloading the first image there. Okay, so you can see the difference between the first exposure and this one here, 60 seconds. You can see more detail in the outer wings here. Okay, so it looks like the second one is stacked. Let's go ahead. So that's 2 images stacked there. It looks like a third one just came in. Making some adjustments to the histogram, kind of bring out different details. So the Orion Nebula, this is known as Messier 42 from the Messier catalog, and this other portion here is M43. Okay, so here comes in the fifth. Yeah, I got another question from Jim as to whether I choose the stars to guide on or whether it's automatically done. And the answer is it's automatically done. Now the ASI Air Pro is a very integrated package of different routines that pretty much take care of everything automatically. And I've had great success with it. It just seems to work. You know, a lot of times you'll see people on live streams spend a lot of time troubleshooting their equipment rather than actually getting images, but the ASI Air Pro is just, it just works. I really like it. So that's a 6th image that's come in. Now I wish I would have a better view of the PixInsight screen. Because for some reason in the OBS software suite, it's not showing anything when I bring up the window that it's in. So I'm having a technical glitch there. So my workaround is to actually work with PixInsight on the second screen and just show that screen in its entirety, which sort of works, except I really can't get the detail that I wanted to get to show up on the live screen, so that makes it a little more difficult. Okay, so it looks like we got 7 stacked there now. Let's go ahead and bring up the histogram. Let's go ahead and stretch it a bit here and see if we can bring out some of the more details in the outer wings here. So you can see that now. You can see these kind of details coming out here in the outer fringes of the nebula, and you can actually see now that M43 is merging with M42, whereas in the previous stacks, they because we didn't have enough signal yet, they actually look separated, but you can see they're actually part of the same nebula. Yeah, and Jim, going back to the guide stars too, you can see that it chooses multiple guide stars, so it's kind of averaging them out to give you more precise guiding. And this is the main one down here. But the auto guiding seems to be pretty good. What you notice here, the sudden separation in declination, that's because as I mentioned before, the telescope is a 20-year-old telescope, and the declination gears in it really has quite a bit of what's called backlash, where when you give it a command, it overshoots, and then you got to wait for it to catch up again. So that's what you're seeing here. When it does a correction, you see the backlash. It jumps, too far, and then it's slowly got to move back to the center. When you change directions between north and south is when it's most apparent. It's looking pretty good now with the 10 images stacked. I think I'll go ahead and do 15 images and stop it and save it, and then go back to the James Webb Space Telescope field and take another set of 10 images and see if we can detect any motion. See, we just had another, overshoot in the declination right here. So typically that'll elongate the stars. So when it gets stacked, it'll be a larger star that's not quite round. Luckily, with post-processing, you can go through and eliminate the images like that. So you can throw out the bad ones and not make them part of your live stack. But on this one here, it's showing a stack 12 and ignored 0, so I'm kind of surprised we don't see more of an elongation there. Now you can see more of the swirls coming in here, and see more of the details in M43. See more of the details in this section here, and the difference in colors coming up, which is pretty cool, I think. considering this is all essentially no image processing. This is strictly raw images coming in and being displayed. When I first started doing astrophotography over 50 years ago, one could only dream of this technology back then, because all we had were film-based cameras. So you'd actually sit there and guide the telescope manually, take these exposures on film. Then you'd have to go and develop the film, and everything back then was black and white, where an amateur to do color was just simply out of the question. So everything was done in black and white, and you had to handle the chemicals, processing the negatives, and then once you had the negative, you had to make an enlargement, and it was quite different, I can assure you. And today it's like I said, I'm sitting in the comfort of a heated room, controlling the telescope and taking images that are being downloaded to my computer and displaying them, and furthermore broadcasting it out to anybody who's interested in joining the live feed. That's quite remarkable in a relatively short period of time. And technology is continuing to evolve too. I've seen quite a few impressive things and techniques that people are doing now just with regular cell phones. Hooking up the cell phone to an adapter, putting it over the eyepiece on the telescope, and taking some remarkable pictures. So I wouldn't even venture to guess what it's going to be like 50 years from now. A lot of you might think immediately, well, all the Starlink satellites are going to ruin the sky. But again, as the technology advances, the techniques advance, and you're able to actually remove any satellite trails that show up in your photograph. It's 50 years ago, if a satellite went through your photograph, your entire photograph would be ruined. There'd be no way to remove it, so you'd have to go and reshoot it. Okay, so it looks like we've got 15 there, so let's go ahead and stop the live stack. Let's go ahead and save it. Let's go ahead and stop the auto guider. And let's go back to the preview. Yep, exit. Okay, so now let me get the latest coordinates for the, let's see, so it's roughly 4 hours 10 minutes universal time right now. So let me go back to my JPL ephemeris, and let me go ahead and center it at the, we'll be at 5 hours. Actually, let me go to hours 6:32:13, and plus 1:38:52. Okay, so 6:32. Yeah, they got to improve the interface here a little bit. So down to 13. So 632.13 plus 138.52. Plus 138.52. So 632.13 plus 138.52. Okay, we're good. So let's go ahead and go to. Okay, so it's flew to the target position. It's taken an image, 5-second image. It's plate solving the stars in that image. It's done. So it calculated the true image center and it's recentering it. And it's taken another photograph to confirm that it's centered. Okay, so it says it's centered. Let's go ahead and do a plate solve. It's 632.13, so we're 1 plus 138.22, so we're about half an arc minute off in deck, which is okay. Okay, so let's go ahead and get the auto guider going. Give it a second to settle down. Okay. So the RA is the one we want to watch. The declination will slowly come into view. That's why you see, a little bit of motion when we're blinking the images, because the deck is drifting back into to where it should be. Okay, let's go ahead and do another auto run. Let's go ahead and do 10. While the images are taken, I'm going back, looking through the animation stack. That I had before, and I'll select the best image from each of those sequences of 10. I got a question, have I visited IC 434 yet? And the answer is no, that's coming up next. And Jim is asking a question, if there's backlash in the RA also, is the backlash really small for RA? There is a backlash in both the gears. It's a 20-year-old telescope, and it's mass produced, so the quality compared to mounts of today is really no comparison. But the RA, the backlash really won't occur until the telescope passes the zenith point. That means when it passes straight overhead, and then all the weight will shift from the eastward direction to the westward direction. Then you'll get some backlash there. For right ascension, the typical error is what's called periodic error, and that's just imperfections between the worm gear and the main gear. That's repeatable because it takes about 15 minutes for the worm gear, which is a smaller gear, to make one complete rotation. So every time the gears come to certain sections of the gear, the error tends to be repeatable. So the auto guiders and the auto guiding software are smart enough today to actually predict when the next error is going to occur because of the periodic error, and then compensate for it. So primarily for what we're doing tonight, the biggest backlash error is going to be in declination. So let's see how we're doing in our sequence. Okay, looks like we completed the sequence, so let me go ahead and bring in the third sequence, download it. Okay, so it's copying across. Well, we were talking about, you know, the old telescope, getting numbers like this, you know, 1.5 arc seconds. That's, frankly, I didn't think I'd ever be able to get this old LX200 to get the numbers down below that, especially with a short focal length refractor as a guide scope. I had used what's called an off-axis guider, which is a prism that picks off a portion of the light coming in through the main optical tube. This is what's going on here. I'm copying the files. But it has a disadvantage that the focal length is the same as the main telescope. So as a result, your guide's field of view from your guider sensor will only allow, you know, maybe 1 or 2 guide stars to show up at any given time. Another disadvantage is that towards the edge of the field of view, the stars are distorted, so they're not, you know, pinpoints. So that makes it more difficult for the autoguider to work. So oh shoot, let me. No, I'm still copying the image now. Yeah, sorry, I'm trying to have problems identifying those images that I just took. And mystery solved. It changed the name. Instead of calling them target, it's calling it to what the previous target was, which was M42. So now that I've figured that out, I'm copying the correct images to the main computer. So hopefully in a few moments here we'll have the latest animation stack going. Okay, it's about halfway copying the images. Okay, we're just about there. Okay. Okay, so I'm going to load those into the stack. There we go. Let's go ahead and animate those. Okay. Yeah, again, nothing is obvious from that third stack, so let me go ahead and stop it here. And let me go ahead okay, let me 18 to 17. Okay, okay. That's not going to work because I got to actually align the star images. So let me bring up bear with me, I'm going to align those images with each other in PixInsight. Okay. Yeah, unfortunately you can't see what I'm doing in PixInsight because I'm not able to. Now I just invoked the star alignment routine, so you can see that status, and it looks like it didn't like that. Try it again. Change some of the parameters and it looks like it might be working. Okay, it did, so let me go ahead and bring in the aligned images. For some reason they're not outputting the aligned images. I don't know if that's because the images haven't been calibrated. I'm just running the raw images. That's not very... Well, I don't want to troubleshoot that here, so let's only go to IC 434 and do a quick live stack there. Let's turn off the auto guider. Okay. So all the you guys who have been waiting for IC 434, we're going there. So it looks like the biggest problems I'm having tonight is with the interface for the live stream and getting some of the PixInsight functions to work. So that's something for me to troubleshoot. so it'll be resolved by next time. Okay. So it looks like we're there. Let's go ahead and get the auto guider going. A lot of stars there. You notice on the auto guider, it's smart enough, it knows not to pick the brightest star there, because the brightest star is saturated, so the software is not able to precisely determine the center of the image of that star. So it goes for the fainter ones that it's easier to detect where the center is. Okay, so let's go ahead and let's go to live. And let's do the same thing. Let's back duration 60 seconds. Yeah, let's do the same thing. 60-second exposures. Because right now in the first stack you can see that the image just appears to be stars. Now I can say from experience that IC 434, also known as a Horsehead Nebula, is a very difficult object to see visually, even in a moderately large telescope like my 12-inch. You need just the best conditions to see it using the right filters. Now, PixInsight wasn't outputting the stars from the star alignment routine. I'm doing something differently tonight that I normally don't do as part of my work process. So normally when you're processing a batch of image from a given night, you first do what's called the calibration of the images, where you take the images and subtract the dark frames, subtract the bias frames. Those are all subtle frame differences that show up because of the heat and the sensor, and some of the other effects that are there because of the nature of the CCD image. So you go through the calibration first, and then the second part is that the raw image shows up in PixInsight. It hasn't been what they call debayered into the color components, so the image is actually stored in a stack of red, green, and blue layers. So it has to be, as part of your pre-processing workload, has to be debayered into the color components and made up into a color image. And I hadn't done that. So I'm thinking that the star alignment routine might not be working on the raw image. That's something for me to again investigate and figure out what's going on before the next time. Okay, it looks like we got 2 images coming in. And I don't know if you can see it, but you can kind of see this area right up here. You're starting to get some nebulosity around that one star. And then if you just look in the center, you can just kind of see the Horse's Head starting to appear there with a second image. Let me go ahead and see if I can play around the histogram and see if I can bring out some of that detail. There we go. And you can kind of see some reddish color here. Okay, it looks like a third image is coming in. Okay. And with that third image, you can see a little bit more detail in the Horse's Head. You can kind of see this is the back of the head here, and then the front is coming up here. But what's amazing, what you're looking at here, you'll notice that there's a lot more stars on this side of the image than there are on this side of the image. And that's the whole physical nature of the Horsehead Nebula. Because in reality, beyond this nebula, star densities are they're about the same. So there should be the same number of stars showing up here and over to here. So what's happening is this whole left side here is a big dark nebula. So it's actually a nebula that's in front of the other stars, so the starlight from the other stars can't pass through it. But on the right side here, where the dark nebula doesn't exist, and you can see the reddish colors from the emission nebula that makes up it as well. Okay, and so image number 6 is coming in now. It's downloading. And so it was a little more detailed, very difficult to see it, but if we adjust the histogram, that's a little bit too much. That's the wrong direction. Let's go ahead and reset to auto here for a second. See if the image 7 is coming in, but it's washed out with the auto histogram. So let's go ahead and reset it here. Let's reset the black level. Maybe a little bit more. There we go. You can kind of see more colors now coming in. There, now you can really see the horse's head emerging. Is that cool or what? Yeah, look at those guiding numbers too. I mean, that's for a 20-year-old telescope with a small guide scope on top of it. That's pretty amazing in itself. So I'm very pleased with that. And now if you notice that the graph just got bigger all of a sudden, that's because the auto scale is going down to smaller values for the upper and lower bounds. So you got plus or minus 4 arc seconds being displayed here. And before that it was plus or minus 8 arc seconds. So it's kind of automatically zooms in as your guiding gets better. And there we got a little bump in the declination. Now I know there are people out there that actually go through, you know, tear apart telescopes to minimize the, these type of errors here, with the backlash. There's software compensation to a certain extent, but if your hardware, there's just so much that you can do with software to correct problems in hardware. So my personal preference is, instead of spending all my time working on the telescopes, actually going out and taking images, and the ones that are bad because of these defects, just throw them out and just stack the good ones. Again, 50 years ago you couldn't do that, because you would typically take one continuous photograph for 30 minutes to an hour. So your camera, the shutter would open up, and you would just have to stay focused, physically at the eyepiece of your guide scope, peering into the telescope and trying to keep the faint guide star perfectly centered on the crosshair in the eyepiece. And that was very difficult, because any momentary hiccup, if you're not paying attention to the star moving, and then you overcorrect, that eventually will show up in your one continuous photograph. So that's why one of the big evolutions of astrophotography was in the late 80s, when the Santa Barbara Instrument Group introduced the ST4 auto guider. So that essentially took the imperfections of a human guider out of the loop, and everything was done electronically, with better precision. And now, today the equipment that is out there is just absolutely, remarkable. and you can tell that by the astrophotos that are being produced and displayed on the internet. Okay, so there's 13. Okay, so that's a stack of 14 so far. Again, we'll go ahead and go with the 15. And I know we've been going just under 2 hours now, so probably what I'll do is go ahead and end the live feed and then go back and take some more images of the James Webb Telescope field, and then do some post-processing on the images and see if I can pick it up doing it that way. So there's 15. Let's go ahead and save it. And then yeah, so that was 15 1-minute exposure, so that's about 15 minutes total on that one there. And let me show you, that's what it looks like with a couple of, I think 1.5 to 2 hours worth of data there. You can see quite a bit of difference there. There's the raw and there's the processed. So that's a 15 stack and then processed there. And let me see if I got an M42 I can share with you too. And there's M42. Now the effective focal length on this one here was a little bit less, so it was operating at f6.3 on this one here through an 8-inch telescope. But you can see the detail that comes out, and down here is what's called the the Running Man. Or down here, I don't know if you can see my cursor or not, but yeah. So I'm going through the comments now. Yeah, you're welcome, Jim. Happy to have done it, and I'm a little bit disappointed that the space telescope wasn't obvious in the images, but it's moving, surprisingly slow amongst the background stars. So I'll have to do some post-processing and then I guess present the results in a follow-up video that I'll post here. Yeah, and here's another comment that hopefully within the next several months the telescope will be cooled to the optimal operating temperature. Yep, that's the goal. Yeah, no, I have great science is going to come from the James Webb Space Telescope. I've watched some of the reviews on what the plans are for, and it's just all I can say is great things are going to happen, so we can all look forward to that. So, and you're right that IC 434, that's 1,500 light years away. So the light that you see coming in for the Horsehead right there started 1,500 years ago, and it's been traveling across space through all this time, and just tonight reaching the sensor that we're able to display it here on the screen. So it's sort of a time machine. So okay, well, yeah, I'd like to thank everybody for joining me again. We had partial success with the live stacking, and need to work on the technique and methodology for presenting the James Webb Space Telescope in real time. But hopefully if we have some more clear nights in the coming weeks, we'll revisit this and try it again with the lessons learned from this one. So thanks everybody, good night, and